So today's lecture is over 3.4, Combinatorics and Probability. So we're really going to have to use this idea of counting in probability. Because probability, we talk about the probability something's going to happen over the total chances of anything happening. So like winning the lottery, what's the probability that I get the winning ticket over all the tickets that can be sold? So we're really going to apply these concepts of permutations and combinations in the idea of probability. And then we'll use probability to analyze games of chance such as the lottery. So to kind of refresh our memory, we have the the permutation formula. This is when order of the selection does not matter. And the combination formula, and this is when the order of the selection, the order of the selection does matter, and here the order of the selection does not matter. So, one of the first problems you're going to have is X amount of people selected at random. What's the probability that at least 2 of them share the same birthday? So, the first example we're going to look at is a group of 3 people selected at random. And then we'll actually do one with more than 3, and you'll actually see. You would think that it's not very likely, but it turns out to be pretty likely. With 3, it's not that likely, but a group of 30, it's going to be over 70% probability that someone shares the same birthday. So let's go through the calculations, and you'll want to remember how to do this because you'll be doing it on your homework. So the sample space size is going to be the set of all possible lists of 3 birthdays. So for the first person's birthday, we have 365 choices. For the second person's birthday, we have 365 choices. For the third person's birthday, we have 365 choices. So the number of elements in S is 365 cubed, and this is going to come up later. So we're looking for the probability that someone shares a birthday with someone else, which would be really hard to compute E directly. So what we're going to do is we're going to use probabilities and compute E prime, meaning no one shares the same birthday. So finding the number of elements in E prime, we're actually going to use permutations. So we're looking for how many different ways can I rearrange 3 dates in 365. We use a permutation because the order of the selection does matter. The list, May 1st, May 30th, August 23rd, is different than May 3rd, August 23rd, and May 1st. So basically this is the first person's birthday, the second person's birthday, and the third person's birthday, which would be a totally different group than if I rearranged them differently. So I use permutations. And if you wouldn't have come up with this on your own, that's fine. I'm going to give you a formula for it when we get done. So for this example with 3, I do 365 permutations 3 divided by 365 cubed, because that's the number of elements in S. That's the probability of E prime. So the probability of E is going to be 1 minus the probability of E prime, which is going to be this. So I can take this and say generally, or in general, if I want to look at the birthdays with a group of X people, this is the calculations I do. 1 minus 365 permutation X over 365 to the X power. So now let's look at doing that with 30. This one is number 1 in your book, and you can actually see the answer is over 70%. So I'm going to have 1 minus 365 permutation with 30 over 365 to the 30th power. So 30 spots, that's going to be really time consuming to take 1 minus 365 times 364 times 363, etc., right? Because I'm going to go down to 30 spots. That's going to be really time consuming. Divided by 365 to the 30th power, which is just a large number. So this is why knowing this number from the formula is going to be important. So if I want to take 365 permutation 30, that's 365 factorial over 365 minus 30 factorial. So I'm going to plug in my calculator, 365 factorial over 335 factorial, and I'm going to leave that in my calculator because then I'm going to take 1, so let me pull up my calculator. I'm going to take 365 factorial, which is a huge number. You know, there's 778 points that move the decimal. Leave it in your calculator as that, and it's all going to come out in the end. So divided by 335 factorial, still a huge number, not as huge. I still have 76 places to move my decimal over. So again, you're not going to want to do these by hand. You're going to have to use a calculator. So this is my permutation. Now I'm going to divide that by 365 to the 30th power, which is just a really large number. When I divide it by it, I should get a really small number. Now, my final answer is 1 minus that number, which tells me 70.6%. So if I look at my calculator, I get approximately 70.63%. So I'll just say 63%. So that's over 70%. Over 70% chance that two people share the same birthday in a group of 30. So you're going to have problems, maybe they're 28, 27, 31, 32. You're going to do along the same work. So you want to remember this formula here and be able to calculate them and put them in your calculator correctly. So moving on, we'll have the next type of problem we have are potentially lottery problems. So we all know the probability of winning the lottery is really small. But let's look at how we calculate it. So we have this 644 lottery, meaning you pick 6 numbers out of 44. So the numbers range from 1 to 20 or 1 to 44. So the probability of winning first prize is getting all 6 numbers correctly, and the order of the numbers doesn't matter. So you know that this is a combination, right? So the order doesn't matter when you play the lottery. In this lottery, the order doesn't matter. So the probability, so I need 6 numbers and I'm picking 6 of them. There's only 6 winning numbers. I need to pick all 6 of them to win first prize over the 44 numbers choosing 6 of them. So if I go through and do that, 6 choose 6 is 1, over 44 choose 6, which would be 44 factorial, over 44 minus 6 factorial times 6 factorial. So if I go to my calculator and I clear it and I do 44 factorial divided by, if I do open parentheses, 44 minus 6, close parentheses, factorial, and then divided by 6 factorial. So the probability that I win first place is 1 over 7059052, 7059052, 052. So the event of winning second prize would be picking 5 of the 6 numbers. So includes 5 of the winning numbers. So I have 6 winning numbers and I'm choosing 5 of them times the losing numbers, which would be 44 minus 6. So if I do 44 minus 6, that tells me there's 38 losing numbers. So I can pick any of the 38 losing numbers over the total number 44, choose 6. So my number on the denominator is the same, 7059052. And on the numerator, I do 6 choose 5. So that's, if I do that on the side, 6 choose 5, that's 6 factorial over 1 factorial, 5 factorial, so that's 6. There's 6 ways to pick 5 winning numbers from 6. So we get 6 times 38. So if I go to my calculator and I take 6 times 38, I get 228. So my answer here would be 228 over 7059052. So this would be your answer, the probability that you win first place, or sorry, the probability that you win first place and the probability here you win second place. Now if you plug this in your calculator, and if you give it to yourself in a decimal, right, 1 divided by 7059052, you can see that it's -7. So 0.12345 That's the probability that you have, that's the probability that you win the lottery if it's 644, where you have to pick 6 of the winning numbers to win first place. So that's not even 100th or millionth of a percent, right? 1, 2, 3. So that if you played the lottery 7 million times, 7,059,052 times, you're expected to win it once. Here, if you play the lottery 7,095,502 times, you're expected to win second prize approximately 228 times. The 535 lottery, you're going to, along the same lines, right? So you have 5 choose 5. That's the only way to get all winning tickets. And then you have 35 choose 5. And you want to leave your answer as a fraction. The winning second prize would be 5 choose 4 times 30, because there's 30 losing numbers over 35 choose 5. So the nice thing on these problems, once you find the denominator, it's the same in both part A and part B. So I'll let you guys work on some of those. The next thing that might come up on WebAssign would be Keno. And this game contains, go back here and fix this. I don't know why that cut that off. So we have a game. This is generally played in the casino, and it has a board that has 1 to 80 spots on it. And you buy tickets that have anywhere between 1 to 15 spots, usually 6, 8, 9, or 10 spots of those 80. So the casino chooses 20 winning numbers. It uses a mechanical device to ensure a fair game, so it's randomly generating 20 numbers, and if sufficient amount of numbers win, then you have an appropriate payoff. So you have something like this. So what's the probability of winning 8 winning spots when you get to mark 8 spots? So if you get 8 winning spots, you get more money than if you have 4 winning spots. But we're not really going to be concerned with the money. We just want to talk about the probability of winning. So 8 spots are marked and 20 winning numbers are listed. So out of 20 winning numbers, what's the probability that you choose 8 of them over 80 numbers total choosing 8? So this is going to be your probability here. If you have a scientific calculator, you can actually hit this. You have 20 choose 8 over 80 choose 8, and it will give you the probability right there. 7 winning spots, you're going to have to do a little bit more calculations. So you have, out of the 20 winning numbers, you are going to pick 7 of them times 60 of the non-winning numbers, because one of them is going to lose, over 80 choose 8. Oops, 80 choose 8. Because, sorry, 80 choose 20. That's something I didn't do right. Over 80 choose 20. So going back here, 80 choose 20. Okay, sorry about that. It's not 80 choose 20, it's 80 choose 8. So I want to fix that, and then in a minute I can explain it. Choose 8. So you're only picking 8. So you have 20 ones, this is the winning ones, over the total. 80 is the total, and 20 win. So this would be that I win 8 spots. Now if I look at 7 winning spots, I'm going to say out of the 20 that win, I'm choosing 7 times 60, and you can say 60 choose 1, over 80 choose 8. 80 choose 8. Because I'm only choosing 8 of them. 20 of them are winners. 60 of them are losers. 7 plus 1 is 8. So now let's look at 6 winning spots. So if I go to this one at the 6th winning spot, so I would have 20 choose 6 times 60 choose 2 over 80 choose 8. I might recommend that you get a scientific calculator on this section, and I actually don't have a scientific calculator because I got it today. Scientific calculator will have an N choose R and an N choose, or NPR. These will have these buttons, and you can simply push this button, times this button, or find this number, find this number, find this number, then take this number times this number over this number, and it'll give you a decimal answer. If you're doing it in the calculator, it's a little bit more work. So if you have a scientific calculator, a lot of times they're like 10 to 12 bucks at Walmart or Target, various other places. So if you have one and you don't know where these buttons are, you can usually Google where's the permutation button, or you can ask someone, and usually you have to hit shift and find it. So again, fewer than 4 winning spots. This is actually kind of hard to calculate, so what you're going to do is you're going to take 1 minus the sum of your answers above. Right, because you're either going to win 0, 1, 2, or 3, or 4, and that would be this category. So instead of calculating 4 different 0, 1, 2, 3, and 4, instead of calculating 5 different probabilities and adding them together, you can take 1 minus the sum of these numbers. So be careful because you're rounding to 8 decimal places. So you need to be able to see the 8 decimal places in your calculator. So if you have it in scientific notation or something, you have to be careful. Because if it gives your answer as like 1.0 times 10 to the minus, let's see, minus 8, that's really 0.1, 2, 3, 4, 5, 6, 7, 8, something like that. So if it says round to 8 decimal places, it doesn't want it in scientific notation. Okay, so we're getting close to being done with this section. And the next 3 examples I'm going to go over has to do with knowing permutations. So you order 14 burritos at a Mexican restaurant. 6 of them are hot and 8 of them without hot peppers. So 6 have hot peppers, 8 have without. But the restaurant forgets to label them. You pick 5 burritos at random, and you want to find the probability exactly 1 has hot peppers. So to find the exactly 1 has hot peppers, so 6 of them have hot peppers. So 6 choose 1 over 14 choose 5. So you're picking 5 of them. On top here, this would be 8 choose 4. So this is the calculation you're going to do. Exactly one has hot peppers. 6 of them have hot peppers, and you want to pick one of those. 4 of them, you want 4 of them not to have hot peppers, and only 8 of those have not hot peppers. Over 14, choose 5. So if you look at this number plus this number, let me kind of highlight it here. If I have this number plus this number should equal this number, and let's put it in red. This number plus this number should equal this number. So this is one example, but another example, at least 2 have hot peppers. At least 2 have hot peppers. You could find the probability that 0 have hot peppers plus the probability 1 has hot peppers plus the probability 2 have hot peppers, which would be hot peppers, and I have 8 with hot peppers. So you could do 8, choose 0 over 17, choose, you're picking 3, times 9, choose 3, right? Plus 8, choose 1, times 9, choose 2, over 17, choose 3, plus 8, choose 2, times 9, choose 1, over 17, choose 3. So the calculations here can be kind of intense. You're either going to get 0 with hot peppers, 1 with hot peppers, 2 with hot peppers, or 3 with hot peppers since you're picking 3 burritos. So what you can do is you can find 1 minus the probability that you have 3. So this is going to be the same as 1 minus 8, choose 3 over 17, choose 3. This is usually a little easier to calculate. At least 2 have hot peppers. You're looking at the case where you have 0, 1, or 2. Or you can do 1 minus the chance that you have all 3 of them with hot peppers. At most 2 have hot peppers. At most 2 have hot peppers. At least 2 have hot peppers. Oh, sorry, I'm switching that here. At most 2 have hot peppers would be this example. So let me actually, at least 2 have hot peppers would be the probability that 2 of them have hot peppers or 3 of them. So the probability 2 have hot peppers plus the probability 3 of them have hot peppers. So you do 8, choose, in this case, the numbers change, but, sorry, I messed it up there. So at most 2 have hot peppers. It gives you the instance where you have 0 with hot peppers, 1 with hot pepper, or 2 with hot peppers. So at most 2 have hot peppers. At most 2 have hot peppers. So you can have 0, 1, or 2. At least 2 have hot peppers would be 2 have hot peppers or 3 have hot peppers. So you have to find the probability of 2 having hot peppers plus the probability of 3 having hot peppers. So hopefully I didn't confuse you too much on that. If you go to your assignment, they have watch it buttons. So if I go to your assignment, I go to Open Student View, and I go to 3.4. A lot of these have watch its, so especially with the hot peppers, you can kind of watch it, and if you have the volume, and I don't have my volume plugged in, they will actually go through here. Now keep in mind your numbers can change. So be careful with the wording. Like I messed it up on the notes, and sorry about that. So be careful. It says at least 2 have hot peppers. So they'll go through and actually show you how to do this. So let me know if you have any questions, and if I need to go over one of these again or explain it, I can make a video of it specifically. Good luck with this section.